All right, back from break. We were talking about heat pumps. I was saying how enthusiastic I am about these. It's a way to replace a lot of fossil fuels. You know, a lot of our furnaces, a lot of our home heating is based on using natural gas, which of course generates carbon dioxide. It's very efficient. And so we'll talk a little bit more about how efficient these heat pumps can be. But this is an excellent diagram to come back to. I think most people have, I'm guessing, you guys are all like science and engineering majors, so you're just inherently curious, and I'm sure you've pulled out your refrigerator and found out that there are these coils on the back, or if they're hidden, there's at least a hot region on the refrigerator that releases that energy. Okay, let's take a look. I was also going to mention with the issues with carbon dioxide and our concerns about continuing to put carbon dioxide into the environment, many areas now, when I was looking at my heat pump, looking around at different heat pumps to have installed, I came across an article saying that British Columbia, for example, no longer allows the sale of natural gas furnaces. And that's a pretty harsh environment, right? When you think in terms of the winters there, it's not a Bay Area winter. Temperatures really get cold, but they're switching over. They've come up with these heat pumps that can operate even in really low temperature conditions. So they're going to, generate a bunch of electricity through hydroelectric. There's a lot of hydroelectric energy possibilities there, or through wind or whatever. They're planning for the future and eliminating the use of fossil fuels like natural gas. All right, for a heat pump, we've got that same diagram, but all the arrows switched directions. So notice what happened is we're drawing thermal energy away from a low temperature region and transferring it to an already high temperature region. Now, that means we can use the same formulas, sort of. Now, we don't define the efficiency of a heat pump as an efficiency, although I'm going to talk about it that way. It's actually strictly supposed to be the coefficient of performance, and when I was looking around at heat pumps for heating, you can also get water heaters that operate on the heat pump technology. You can also get clothes dryers that operate on heat pump technology, and so we're currently in my home, all of our natural gas appliances are ending their life cycle anyway. We have an older clothes dryer, we have an older water heater, we had an older furnace, and with this new, once we're replacing these, we're thinking let's replace them with heat pump technology. So this is called the coefficient of performance, and the heat pump that I have at home right now as a heater and cooler has a coefficient of performance of about 4. So let's see what that means. The coefficient of performance is asking how much heat can we transfer divided by how much work I need to invest. Remember, with a heat pump, I'm not getting work out, I'm putting work in. Specifically, the work I put in is operating an electric motor to operate the compressor. Remember, we got to have a compressor to make this heat pump work. So the COP, then written at QL over W. Now remember, W is going to be the same thing as QH minus QL. That formula still works. And then ideally, the coefficient of performance will depend on the operating temperature. So this is how it actually operates. This is the theoretical formula. Let's look at some examples. So here's a heat engine on the left. Here is a refrigerator or a heat pump on the right. The efficiency here was the work we get out divided by QH. That's QH minus QL over QH. Ideally, QL over QH is TL over TH. This is the efficiency formula. This is the ideal efficiency formula, which can also be written 1 minus TL over TH. Now to do a comparison, the refrigerator, all the arrows reverse. The efficiency we're looking for is to get as much heat transferred. Let's make the QL as big as possible. This is for a refrigerator, divided by work. And that becomes QL over QH minus QL. Ideally, this ratio holds. So every time we write down this ratio of Q's and ratios of temperatures, that's from the second law of thermodynamics. It's saying that ideally, the entropy just barely stays the same, and that would say ratios of Q's are matching operating temperature ratios. So the ideal formula here comes from taking the Q's and replacing them with the T's, because that's what this ratio is. Now, the efficiency for a refrigerator is TL over TH minus TL. So if I'm operating my heat pump in cooling mode, that's the COP. But when we're using the heat pump to heat the house, well, then I'm not thinking in terms of QL, I'm thinking in terms of QH. And QH is always going to be bigger. So ideally, the coefficient of performance for the heating operation would be TH, not TL, and the coefficient of performance itself would be QH over QH minus QL. Let's run some numbers and see what a heat pump might operate like. Now, they're saying we have a freezer. It has a COP of 3.8. It uses just 200 watts of power. How long would it take this freezer to take in an ice cube tray of 600 grams of water? Oh, to freeze it. That's it. All right, let's take a look. So we want to make some ice. All right, there's the freezer. That is a heat pump operating in reverse. It's a heat pump. It's a heat engine operating in reverse. And so we're going to pump heat out of a freezer. There's the freezer. That's the low temperature region. Here is the room. Now the compressor is using 200 watts, 200 joules per second, and the COP is 380. Now strictly, the W's, the QL's, the QH's, they all should be in joules, but we can also just think of it in terms of watts, because it's a rate at which the energy is transferring. So I did put this in watts. I put the QL in watts. That can also be thought of as 760 joules per second. And I use the COP to determine. So this is where the efficiency comes in. If I transfer heat, I'm transferring 760 joules of heat every second. It only takes 200 joules. So rather than generating the heat, which would be a 1-to-1 efficiency at best, I pump the heat. And pumping the heat enables us to be more efficient. So in some sense, what's the COP we have? 3.8. In some sense, this makes it 380% efficient. And that's why we tend not to call it an efficiency. It's a coefficient of performance. But I transfer 3.8 joules for every joule that I invest. So, and again, the heat pump that I have here in my home is somewhere in that range. It's around 4 or something. So here is the ice. It's starting out at 0 as water, but we want to freeze it into ice. So we just want it to freeze. We don't want to lower the temperature anymore. That's just one process, M times L. Here is the latent heat of fusion for water. And it says that we need to remove about 200,000 joules. So how long is it going to take this heat pump, this freezer, to transfer out 200,000 joules? So this is 199,800 joules. And what this told us is every second we are going to be able to transfer out, that's QL, we're going to be able to transfer out 760 joules. And so what it says is 263 seconds. So we're using the full heat pump capabilities of this freezer to just make one set of ice. And I think that's why it's coming out so low. Now, the issue we would run into if this were really a real situation that we were looking at, the difficulty in getting the ice to freeze then would come down to heat conduction. You know, if I put the ice in a plastic tray, plastic is a thermal insulator, that's not going to allow the heat to leave very well. If we really want good thermal conductivity, we need to go to one of those old refrigerators. Maybe you've got one around, but the old refrigerators, the freezer compartment was metal. Now, that was a problem if you went in and touched it, because your finger, your hand could freeze to the metal compartment, which was a little disconcerting. But on the other hand, if you make the freezer with a metal cabinet, then the conduction is really good. If I have a metal freezer compartment and I have a metal ice tray, and that's what I grew up with, everything was metal, and the coolant was running right through that freezer section. You could see the pipes from the coolant running back and forth. That ice froze really fast. When the compartment got replaced with plastic and the ice cube trays got replaced with plastic, it was much safer, but it takes a lot longer for the heat conduction to take place. I'm gonna put that out there. So I think it's better the way we do it now. It was a little exciting to get the ice out of the freezer back when I was a kid growing up. It was like, that ice tray is like frozen to the freezer compartment, and I want to get the ice out, and if I touch the ice tray, I'm going to freeze my hands. That was more excitement, but it probably was. Today's probably a better idea. All right, here we're using a heat pump in the manner I talked about. We're going to take the heat pump and draw in thermal energy from the outside and leave it inside the house. Now, how could I take a refrigerator and turn it into a makeshift heat pump? Well, you take the refrigerator, you take the door off, you turn the refrigerator around, you cut open an opening onto an exterior wall of your home or apartment, talk with your landlord first, and you turn that around and you duct tape it so that it's sealed, and so now the inside of the refrigerator is basically outside the apartment or outside the house. And the coils on the back of the refrigerator are radiating heat into the room. So you can take a refrigerator, empty it out, and again, open up an exterior wall, seal it in really well, get a lot of caulk, get a lot of duct tape, and then turn on that refrigerator, plug it in, and let the warmth from the coils on the back of the refrigerator heat your apartment or your house. And then you'll be comfortable. Okay, don't tell your landlord I suggested that. All right, so here's an example. We've got a heat pump. It's rated at a coefficient of performance of 3, and it's rated to do work. I think it's a 1500 watt work. That's how much work it takes to operate the heat pump. That's what I'm guessing. How much heat can it add to a room every second? If we turn the heat pump around and use it as an air conditioner, what would you expect the coefficient of performance to be? All right, yes, there it is. I was expecting that. Here is the heat pump diagram. And the COP, when it's being used to heat the home, is QH divided by W, because that's what we want. We want as much QH coming into the house. That means the efficiency I can calculate is QH over QH minus QL. The energy we need to operate the compressor is 1500 watts, 1500 joules per second, and the coefficient of performance is 3. So from the, where is that? Right here. From this formula, I can determine the QH is 1500 watts times 3. The heat that's coming through is 3 times as much. It's like 300% efficient. Now that would say the heat, the QH is 4500 watts. It must be that the QL is 3000 watts. So every second it's drawing in 3000 joules of heat from the outside, and it's depositing 4,500 joules of heat inside the house as it operates. Now, when we move it around as an air conditioner, then these numbers aren't going to change. So what's going to happen is, now I'm thinking for an air conditioner, it's QL divided by W. That would be 3,000 divided by 1,500. That would be a coefficient of performance of 2. So when you're using cooling, the coefficient of performance drops by 1. All right, let's go back and kind of finish up the chapter, finish up thermodynamics. Finish up the semester by taking a deeper dive, a closer look into entropy, I guess. And let's make this fun by saying, I don't think anything we talk about here you're going to be required to do in the homework problems or the midterm. So, so don't stop. Don't just turn this off. We'll see what happens. There may be things that I do point to saying, actually you want to be able to do this. This part's a good review in any case. We can calculate entropy changes by taking however much heat has transferred and divide through by the temperature at which the heat transfer took place. If the temperature is changing, then I have to break this down and do it one step at a time by carrying out an integration. Okay? Oh, you do have to do this. I'm sorry. I thought I was a little... So this is kind of a repeat of what we started with. So you guys are still there, right? Wave if you're still there. Okay, good. So the water is at 20 Celsius, and we have water at 50. What if we did this? What if we took these two samples of water, we put them together, and this part of the water dropped and got even colder, and this part raised in temperature? Well, that's not going to happen, but it still could happen based on energy conservation alone. So this doesn't happen. Why not? Well, the second law of thermodynamics says that we move towards statistically more likely distributions of kinetic energy. If we take a bunch of molecules, different samples at different temperatures, and we allow them to come into thermal contact, then the distribution of kinetic energies will approach the statistically most likely distribution. So it's a statistical statement. Anything else we need to say from this? No, that's basically it. So this goes one direction. Nature consistently, persistently is moving towards more and more uniform temperatures at all locations. We're headed towards uniform temperature. Now, when we look at a heat engine or a heat pump, they're saying here that the cycles we've been looking at, basically they've been saying this is idealized. And if, as long as we can draw a path with well-determined pressures, volumes, and temperatures at each point, we can define a well-defined pressure or temperature, we approach ideal efficiency. Okay, so, but in real situations, like if we're operating a car engine, it's not a uniform temperature or a uniform pressure when we have these violent chemical reactions going on inside the combustion chambers. And so the more we can maintain uniform temperature, the better we will do, is all we're really interested in here. And then again, this is kind of what we've already looked at, already talked about, that for any heat engine, we can show using the second law, using the law of entropy, that along a closed path, the entropy changes will be zero for the material within the that's being cycled. Now here's so we did some of these already. So let's go back and let's take a look at one more. So again, the textbook did the heat engines first and then came back and did entropy. But I took a different approach, I guess. I hope you guys think it worked. We did the entropy discussion up front and then did the heat engines. And now we're coming back, and this is going to be a bit of a review. What if I have two samples of water? They're both 50 kilograms. That's a lot of water. Now, since they're the same size, the final equilibrium temperature, we can say, is going to be 22. And so I can use these formulas that we've derived. MC logarithm, final temperature over initial. Everything's got to be in kelvins. Make sure that everything ends up in kelvins. And what we have found, now those temperatures are pretty similar on the one hand. So I would think the entropy increase isn't too large. But on the other hand, they're really large sizes, 50 kilograms each. Anyway, when we calculate the entropy change, for sample A, this is 1423.8 joules per Kelvin. And there the temperature went up. And then for sample B, the temperature dropped just a couple of kelvins. And that is minus 14.2. And notice I kept a lot of significant figures because subtraction is dangerous. So when we add those, I guess it's not subtraction, it's adding a plus and negative number. Subtraction is addition, right? And so I'm adding these numbers together, and it works out to be a difference of 18.7. So the entropy goes up very modestly, and that's because the temperature started out so similar with the original samples. Okay, the total entropy always increases where the heat flow is from a warmer object to a colder object in an isolated two-body system. Okay, yeah, it's basically saying what we saw in that formula. The entropy decrease on the side that started out at the higher temperature will always be less. So this one is going to be less of an amount because we consistently transferred the heat. The heat amount's the same. So there's a certain amount of heat that transferred, and whatever less heat left side B ended up inside A. So the heat leaving and the heat going in, those match, but the temperatures at which they transferred are different. And that's showing up in the calculations. Okay, what about entropy change in what's called a free expansion? So a free expansion here, this is kind of an interesting process. So they're going to say that this process occurs adiabatically and that we have some sample size that initially is in some volume and then it is allowed to freely expand. There's nothing in its way. It freely expands and doubles the volume. So what happens with the entropy for this kind of a process? What happens to the entropy of the environment? Okay, so let's go and do some entropy calculations for this example. So this is what it looks like. Let's say that we have a container, but initially there is a barrier that we've set up and all of the gas molecules are on one side. And then at some point we instantaneously remove the barrier. This is referred to as a free expansion. So let's go back and say there was nothing on this side. And so these molecules now are able to occupy twice as much volume as they were before. There were no molecules there before. There's nothing they pushed against. When we took that barrier out, they didn't transfer any energy to anything. They kept moving at the same speed. So the internal energy is constant. We're not losing any internal energy. This is an adiabatic process. There's no Q that transfers. There was no work done. The environment is not going to be affected by this. Nothing happened in terms of the environment. So this is an ideal gas. There's no change in the internal energy. The Q is 0, the work is 0, the temperature does not change. The only thing that's happened is that we went from a higher pressure with a smaller volume into a smaller pressure with an extra volume. Now, to me, it sounds like entropy must have gone up. even though there was no Q, isn't there a way that spreading the molecules out makes them more random? I would guess that that's got to be the case. So let's take a look and see what happens here. Now we can use a kind of a trick. What we can say is that when we look at point A and point B, the difference in entropy between A and B is the same regardless of what path we take. Back when we started looking at these heat engines and such, and we looked at work and heat transfers, we said that when we look at something on a PV diagram, if I'm calculating work or I'm calculating Q, the path makes a difference. So W and Q depend on what path we took. Whereas internal energy and entropy don't. Internal energy and entropy say, hey, if I start out at a set of conditions at point A, and I end up at a set of conditions at point B, I could take a direct route, I could take a roundabout route, I could take a crazy route, but the difference of internal energy and the difference in terms of entropy at the end of the day will be the same independent of what path I took. Now that opens up a possibility for us to go in and calculate entropy, even though it's not clear any heat changed hands. So what we can do is say the entropy change of following an isotherm. If we use an isotherm to connect points A and B, whatever we calculate in terms of entropy changes for an isotherm will be the same as for a free expansion. So the temperatures are the same because there was no energy exchange that took place between the sample inside the container and outside. So there's no entropy, there's no energy, internal energy changes. So yeah, we can calculate the entropy as if the process was isothermal, even though it wasn't. And we'll get the answer that way. All right, so we'll take an alternate route here in solving the problem. Now, for an isothermal process, if you remember, going back to the formulas we derived, the Q equals the work, and that's nRT ln VB over VA. So it says that the entropy change that took place in those gas molecules would be nR. Now it's Q over T, and the path we took is a fixed constant temperature. When I take the Q formula and divide through by T, the T's are gone. And the entropy then is nR ln VB over VA. Now it said calculate this for 1 mole. So that's the formula. So there really is an entropy change. 1 mole times big R logarithm of, now remember VB divided by VA we set as a factor of 2. So the entropy is going to be nR, the logarithm of 2, and that works out to be, for 1 mole, an increase of 5.76 joules per Kelvin. So there was an entropy increase in the sample. Now the environment didn't even know this happened. You know, the environment doesn't know anything about this process. Nothing pushed on the environment, there was no expansion, there was no compression. So the environment is unaffected. But what this increase in entropy says is, yeah, if you take a bunch of gas molecules that we're treating as independent molecules, and you allow them to occupy a larger volume, that represents an entropy increase. Okay, getting all those molecules back into the smaller volume, that's not going to happen spontaneously, right? It's like herding molecules. So how are you going to get all the molecules back to the other side? It's not going to happen on its own. Now, you might come back and say, but wait a minute, isn't entropy all about statistics? And statistically speaking, if we're very patient, won't there be a time, sometime in the future, just by chance, all the molecules are on this side, and we close that down the middle. Now, that might be a reasonable thing to say if you're working with 5 molecules or 10 molecules, even 20 molecules. You might be waiting a while. We are working with 1 mole. We are working with 6 times 10 to the 23rd molecules, and good luck. You're going to have a lot of patience if you're going to wait until every last one of the 6 times 10 to the 23rd molecules, just by chance, happen to be on the same side so that you can immediately close that off and recover the initial condition. Now, there are these philosophic arguments, right? If the universe, the entropy just keeps going up, is the universe just going to become all this energy randomly distributed, everything's at the same temperature? But you can always make the statistical argument that just by statistical chance, at some point, the universe will reset itself. I don't know. That's an interesting proposition. All right, so there's the entropy change that we see. Now, let's try a couple more examples here. Let's say that in this example, we're taking a red hot, it's red hot, stay away, a 2 kilogram piece of iron. Ooh, let's see what red hot would be. 880 Kelvin, yeah, that sounds kind of red hot. Is thrown into a huge lake. Okay, so the things physicists do, right? So we're going to take this block of iron, it's 2 kilograms, we're going to throw it in a really, not just your usual fire, but a really high temperature fire, and raise the temperature up to 880 Kelvin, and then we're going to toss it into a lake. The lake's at 280 Kelvin. Assume the lake is so large that its temperature is going to be insignificant. Determine the change in entropy of the iron. Determine the entropy change of the lake. All right, here we go. Entropy change in the iron, that's going to be MC ln T2 over T1, where the mass is 2 kilograms. The specific heat of iron, 450 joules per kilogram per Kelvin. The ln of the final temperature is 280, and the original temperature is 880. Put them all in a calculator, and when the iron cools down a lot, it's a good sized piece of iron, the entropy of the iron drops by 1030 joules per Kelvin. Those are the entropy units. Okay, that one I'm feeling pretty good about. I think we accurately represented what's going to happen with the iron. Now let's think about the water. Now the water temperature, they say, it's a big lake. So putting that iron in is not going to do much to the temperature of the water at the end of the day, bottom line. So I can just say Q over T. Now the Q that was transferred is the temperature, the mass of the iron, specific heat of the iron, times delta T, and the delta T here is 600 kelvins. So what that says is the iron transferred 540,000 joules into the water that makes up the lake. So if I take a transfer of 540,000 joules coming into the lake, and okay, here is my worry, here is where I can become a little bit skeptical. All of that heat goes into the lake, and the lake remains at a temperature of 280 Kelvin, that's okay, but locally in the lake, when the hot iron goes in, what's going to happen? Right, we're going to vaporize a bunch of water. So I don't think we can send the iron in as one solid block. That would be too much heat concentrated in a small area, and before the water can circulate and smooth out the temperature, the water right where the iron hits, it's going to go really high temperature, and it's going to vaporize part of the water. I think that's unavoidable. So instead, what we can do is we can take the block of iron and cut it into a bunch of little pieces and throw them all, scatter them independently. That way I'm trying to minimize the water that would actually vaporize, because that's going to complicate things. In any case, what they're asking us to do in the problem is say, if I transfer this much energy and the water maintains a temperature of 280 kelvins. Let's see, what if the iron goes in so fast and then it drops very rapidly? Maybe the vaporization process is small. We should try this. We should try this in physics lab. Anyway, the entropy increase of the lake is plus 1030. Now, again, it's going to be irreversible. If I take this really hot iron and throw it into something really cool, the increase in entropy of the water is going to be much larger than the entropy in a decrease of the iron for that process. Okay, so they keep restating this. It's like, all right, you can see the entropy of an isolated system always goes up. It either stays constant or it goes up. Anytime you mix hot water with cold water, the universe can never be the same. Here we go. Here is what's called the heat death of the universe. If that's what's happening, then at some point, right now in the universe, there are high temperature objects, stars and such. There are low temperature objects, but the universe is furiously running all of the chemical reactions, all of the nuclear fusion reactions, all of the ways that energy can be released are being run through. And once all of those processes are completed, and there's no new sources of thermal energy to be released through nuclear reactions or chemical reactions, then the universe has the possibility of reaching thermal equilibrium. Now, for the universe at large, entropy works kind of backwards. So the gas molecules we've been looking at, if the gas molecules are spread out, that's higher entropy. If the gas molecules are compacted, that's lower entropy. But that's not the way the universe works, and that's because of gravity. So when you bring gravity into the equations, gravity into the calculations, the existence of a gravitational force says, actually, eventually what happens is gravitationally everything is drawn together into high mass objects, and in many cases into black holes. So all of the mass tends to come together. As long as we have objects that are separate from each other, there is still the possibility of operating off of gravitational potential energy. As all the objects combine into fewer and fewer objects, maybe fewer and fewer black holes, the entropy is actually going up as that mass comes together. So the low entropy, for gravitationally speaking, the low entropy for the universe would to have all the particles spread out again into kind of a uniform distribution of mass. And that's what our observations suggest, that in the very, very distant past, in the universe, all of the material, in fact all the protons and neutrons and electrons and neutrinos and photons, were very uniformly spread throughout the universe. So we started, in gravitational terms, at a really low entropy, where all of these particles were just uniformly distributed. So the universe would have been very homogeneous. Any section of the universe you go to, it would look the same as any other section you visited. Everywhere you go, there would be this uniform plasma of particles going back and forth. As gravitational collapse takes place, then we go to higher entropy. So spread out is lower entropy, consolidation into high mass objects is the direction towards higher entropy, from low entropy to higher and higher entropy. Okay, there's a statistical expression too. We've talked about the statistical approach for entropy. Let's take a look at a statistical example. Now this one I promised before, right? This one I promise is not going to show up on any midterms or whatever. And it says this, it says, we can run some statistics on this let's talk about a configuration of atoms as if they were coin tosses. So we can actually go back to, let's go back to this example. Remember this one, the free expansion? Let's say these gas molecules on this side of the room or this side of the room, once we take the barrier down, this half of the room is like tossing a coin and having it come up heads. This half, having the molecule on the left side of the room, is a 50% chance. That's like having a coin come up heads. And having a molecule on this side is a 50% chance, statistically, because they're randomly moving around. That's like tossing a coin, heads or tails. Now, if this were to occur, we start out with this state, and it's like tossing however many molecules are in there. Let's toss that many coins. Now, to get them to go back to this side would be the equivalent of tossing, I don't know, 1 mole of coins, 10 to the 23rd coins, and having them all come up heads. Okay, how likely is that? Well, in this example, we're not taking 6 times 10 to the 23rd. Instead, we are taking just 100 coins. Now, what's the likelihood if we toss 100 molecules, coins, I mean, and they all end up on the left side of the room? So, statistically speaking, having all 100 coins turn up heads would be 7.9 chances out of 10 to the minus 31. How many coins is this? 100. How many molecules did we have in that example? 6 times 10 to the 23rd. So you can see, just running statistical measures of this, how unlikely it is. Now, statistically, interestingly enough, what this statistic does, if we go back and look back to chapter 18, remember that statistics said we actually don't have all the molecules traveling at the same speed. Even though that seems like the most uniform distribution of energy, that is not the highest entropy state. It's not the highest statistically likely state. So there are many, many more ways where we could have some of the molecules going slower and some faster compared with where all the molecules have the same speed. It's very unlikely statistically that the energy would get divided up uniformly where every molecule has the same energy and they're all traveling at the same speed. Instead, statistically we can show that this distribution is the highest entropy. It's the most likely. Now, there's a formula that Ludwig Boltzmann came up with where he calculated entropy in terms of Boltzmann's constant, there it is, times the logarithm of, here they're using W, and W has to do with the number of ways that that particular configuration could happen. So, in this case, how many different ways could we take 100 coins and have half of them end up on the left side of the room and half of them end up, 100 coins and have half of them end up heads and half tails? Or molecules where 50 of the molecules are on one side, 50 molecules are on the other side. Now you're thinking, that's actually pretty likely, right? As long as I don't label individual molecules, all I'm requiring is that we take a snapshot and at some instant in time, half the molecules are on one side, half are on the other. How many ways could that happen? And it turns out it's 1 times 10 to the 29th. And so the probability of being right at 50 molecules and 50 molecules, that's an 8% chance. That's remarkable. That 50-50 division of molecules, just statistically, is going to happen 8% of the time. Now, what happens if we have a deviation where we got 55 on one side and 45 on the other? Even that's happening at a 5% rate. So you can see what's happening here is almost all of the probability would say that the number of molecules, just by having them move around randomly, the number of molecules that are going to be on the left side compared with the right side is not going to be much of a difference. Most of the probability is going to be between 40 and 60. You know, almost always it's going to be in that narrow range. So what Boltzmann said is you could take this number of configurations, you could take the logarithm, and that would indicate the entropy. Now the logarithm of 1, if there's only one way that configuration could happen, the logarithm of 1 is 0. So this is considered to be 0 entropy, as is this. Working just from 100 molecules then, we can see how the entropy develops from no entropy for these extreme microstates, and then in the middle, if I calculate the entropy there using the k logarithm of w formula, it's going to be much larger. So we could do that calculation. All right. What that also shows is that, you know, you might think, well, wouldn't it be statistically more likely to have every molecule to have the energy just evenly distributed, so that every molecule gets exactly the same kinetic energy and the same velocity? And again, there's really only one way that can happen. The entropy of that would be extremely low. That is statistically not very likely. So at any particular given instant, there's going to be a distribution of different energies, and as collisions happen, you know, molecules that had low kinetic energy become high kinetic energy molecules, and vice versa. So that distribution that we calculated back in chapter 18 is kind of amazing. That is a way of going in and looking at all the quantum states, carrying out a statistically most likely calculation, and predicting that distribution. When we go in and measure the distribution of speeds or kinetic energies, they match. So it really works. Now, we do want to come back and look at one more example with this entropy formula based on statistics. So it's not based on thermodynamics, it's just purely based on statistics. If you remember the free expansion that we did a couple of slides back, we did a free expansion and we got a formula for the increase in entropy based on an isothermal process and how volumes and pressures were affected. I think it was mostly volumes and number of moles. Now what we can do is actually do it in terms of statistics using Boltzmann's formula. So here we go. Same idea. We've got a certain number of quantum states here. When we take the barrier down, now the atoms or molecules there's twice as many quantum states available to them. And so what we can say is that now the number of ways that n molecules can be configured around g quantum states is g to the n power. So that becomes a statement of how many different ways could we arrange the molecules. Now, this is assuming that the number of quantum states is actually much
higher than the number of molecules. And in things like air, that's true. So if we go through and calculate how many quantum states there are many, many more quantum states than there are numbers of molecules, and that means it's likely that any molecule can go into any state that's available. Anyway, this tells us how many different configurations there would be, and so I can take that expression and plug it into this formula. Now for picture 1, that becomes k ln of WA, and that becomes k ln of g to the n, g of A, where g is the number of quantum states. For picture B, it's k ln, same formula, but now we have more quantum states. So if I do a delta S calculation, like we did before, that becomes SB minus SA. Well, there's a common factor of k, but I get the logarithm of W minus the logarithm of WA minus the it's backwards. Logarithm of WB minus WA. So we went from A to B, And so that's the order we want to put that in. Well, differences of logarithms means that we would get the logarithm of WB over WA. Now, when I take WB over WA, that's G sub B to the n power over G sub A to the n power. That becomes the logarithm of GB over GA to the n, and using the properties of logarithms, I can bring the n out in front of the logarithm. And it says that the delta S, based purely on statistics, gives us n times k ln of VB over VA. Now, the number of molecules times Boltzmann's constant is the same thing as the number of moles times big R, times the gas constant. And that says, oh yeah, that's the same formula. So in that earlier example, we calculated the entropy based on, I think it was number of moles and the volume going up by a factor of 2. This time, we're saying that because the volume goes up by a factor of 2, the number of quantum states also goes up by a factor of 2, and we can use this statistical formula to show that we get the very same formula. So it's going to come down to the natural logarithm of the ratio of volume. So kind of interesting. You can do this all statistically. Now this formula that that Boltzmann came up with, Boltzmann worked at the University of Vienna in Austria, and if you go to the grave site in Vienna, on the tombstone for Boltzmann, there it is. It's the entropy is equal to K ln of W. So Ludwig Boltzmann made an enormous contribution to our understanding of statistical mechanics, thermodynamics, and understanding atoms and molecules and their energies. And this is the formula that I guess he chose, or people chose, to represent kind of a culmination of the work that he had developed. So a lot of stuff in this chapter too. So chapter 19 and now chapter 20. A lot of stuff we've looked at. We've wrapped up all of the material from the textbook now. So whatever questions are coming up with any of these thermodynamics chapters, stop by office hours and we'll get those looked at.